No one forgot everything in the vacation?
Sir, we were discussing about the flow stress, average flow stress, and we did some numericals last class, sir.
Yeah, yeah. Okay, okay, fine. So we have discussed about some properties of the material when we are making the metal forming. For example, the we talked about the yield strength, then ductility, then temperature, then we talked about the friction, then strain rate, then what you Amal told about the flow curve or the flow stress, and then based on some numericals. So when actually we are talking about the metal forming or the deformation, so only just I put in a in a different perspective. So the importance to the creation of the useful shapes by plastic forming process is the control of the mechanical property by the metal working process. Because every time you have to control the mechanical property. If you cannot, because sometimes we are thinking that only we will do some process or we will follow some process. No, because you have to follow that goal also. What should be your aim? Okay, so for example, when you are talking about the low yield strength or the high ductility, these are also you have to focus on. So that's why I prepared here or I told here, you have to control the mechanical property. For example, blowholes and the porosity in a cast ingot may be eliminated. Okay, so maybe sometimes I remember you were asking about how to relieve the internal stress. Okay, so you do not think about only the one process is there, heat treatment, but at the same time, if you want to relieve the internal stress, or maybe if because how the internal stress you are creating or you are generating, because whenever you are changing the temperature in the metal, then you are finding some internal stress. So similarly here, if you in the metal forming process or in the ingot, whenever you are preparing, and if you are getting some blowholes or the porosity there, so you can use the hot forging or the hot rolling to improve the, and you have to eliminate that one if you will use the hot forging or the hot rolling process. And also you have to improve the ductility and the fracture toughness. Okay, so there are, based on your material, based on your process, then you have to use that particular or typical process. In many products, the mechanical property depend on the control of the strain hardening. Okay, so these are also we have discussed about the strain hardening, and based on that also we have done some application or the numericals. In other instance, precise control of deformation, temperature, and strain rate. Because every time I'm focusing, you have to do everything in precisely. You cannot tell that, no, sir, just only I need the process and I will do something, I will add, and something I will get the product. No, you have to do very precisely. Otherwise, it will be very difficult for you to control the parameter because you do not know what should be the or what is the initial parameter you have and what should be the final parameter you have. Okay, so you have to make it precise control of deformation, temperature, and strain rate whenever you are doing any kind of processing. So there are a lot of process actually. So when we have probably in the last class or maybe 2 3 class before, I talked about the bulk deformation. Then we talked about the sheet metal working. So there also we have differentiated the rolling, forging, extrusion. So here also we made it in another way, how, or in other words, how to classify or how to categorize depending upon the force applied. Okay, so when we are applying some force, I just put again some schematic diagram, probably that when initially I put this probably same or maybe little bit of different. So I just categorize here in 5 categories. So one is a direct compression type process. For example, the forging, the photo also I have shared in the beginning, forging and the rolling. Then second one, you have the indirect compression process. So you are getting here like wear drawing or the tube drawing or the extrusion. Then the third one, we have the tension type process. For example, the stress forming. So that means you are putting a die here. Then in the both side, you are just stretching. Okay. And the fourth one, we have the bending process. So these are also we have explained in before. So that means if you have a straight rod or maybe straight sheet, if you want to make it with some angle. Okay. So that means you are making some bending movements there. Then the last one, we have the shearing process. Shearing is like, this is equal to cutting, but you have a big die or maybe you have a punch there. Okay, so based on that punch, because cutter and the punch both are different. So whenever you are putting some punch there and you have to cut this piece because this is a cantilever. Okay, so that means you are applying the force here, and also from the bottom side you are applying the force here. So that means this metal or this sheet you have to cut. For example, when we have the rolling, very long sheet is coming, but you have to stop somewhere. So that means you have to cut there. Okay, so these are the basic categories depending upon the force applied, and these are we are calling typical the forming operations. Right? Is it clear?
Yes, sir.
Okay. Yeah. So now I just put one deforming processing system, like in metallurgical aspect. How probably in the next class I will show the recovery crystallization, how the grains actually, the grains, for example, initial grain you have when you have the undeformed metal. Here you can see in the left hand, this is the undeformed metal, and the right side you have the product. Okay, and this is the tool you have in the bottom, and in the top you have the tool, and you have the metal piece here, or the total sheet here, and this one or this portion will be the deformation zone. Okay, so that means this portion only you are deforming, you are not deforming here. So this is called as undeformed metal or the undeformed zone, and you have the force here on the top side and the bottom side. Okay, and you are when you are putting the metal inside these two die or the two tool, and you are using the lubricant or the lubrication system. Also in the last class we have talked about the lubrication system. Okay, you are getting the product here, and the same time whenever you are putting the lubrication system and you have the metal piece, you are applying the force in the both the side, and you are generating some heat there. Probably also we have talked in the machining process in the last semester. So here also you are getting some heat, or you are generating some heat here. Then at the same time also you are considering some friction there, because you are pushing the material with this with the help of or with the use of this tool or the die in the both side. So you are getting some friction also there. So this kind of parameter all you have to consider whenever you are doing any kind of the forming process. So I mentioned here the plastic working process, which are designed to reduce an ingot or billet to a standard mill product of a simple shape, such as sheet, plate, or bar, are called the primary metal working process. So I think in the beginning also I have asked you what is the basic difference between the primary mechanical working or the metal working and the secondary mechanical working. So the forming method, which produce a part to a final finished shape. Okay, so whatever we are getting from here, so these are known as the secondary mechanical process. So in other words, maybe if you will find or if you will go to the different book also, they are mentioning the first category, the primary mechanical process is known as the processing operation, whereas the secondary mechanical work process is known as the fabrication, because sometimes this word also we are using, the fabrication process or the the processing operation. Okay, so these are the basic difference between the processing operation or the primary mechanical working process, and the next one is fabrication or the secondary mechanical working process, right? And here also I mentioned the deformation zone already. So whenever also you are talking about the metal forming or the deformation zone, you are also considering the distribution of stress and the strain and the velocity, and at the same time also you are thinking about the pressure or the overall pressure. These are also we have talked in the previous classes. And the applied forces must develop yielding in the material, but the stress must not locally create fracture. Okay, for example, you are not, if you remember that stress strain diagram also I have shared in the beginning of the class, you are only considering in the mechanical deformation zone. You are not considering the elastic deformation zone. We are considering in plastic deformation zone, but we are not going towards the fracture or to the neck side. Okay, we are not going that side. So such metallurgical phenomena are the strain hardening. These are already we have discussed, and the recrystallization and the fracture as also important. Okay, so we have to think about the recrystallization, then the recovery, and then also the grain growth. Maybe I will share one slide maybe in the next class. And one more important thing is that the flow stress of the material will be a strong function of the strain rate, and the temperature, because also we have discussed about the flow stress. Okay, and the equation the YF equal to K epsilon to the power N. These are also we have discussed. Fine, is it clear? Yeah.
Yes, sir.
Okay. Yeah. So now maybe we will just go a little slowly. Probably I do not know whether you know this this kind of derivation, because already we covered in composite materials when I have taught in the previous semester. Maybe for the new students, I am not aware of whether you have done this kind of derivation in composite material. But still, I put very simply small equation. So consider an element, because you have to assume something. So consider an element in a tensile test piece in uniaxial deformation and follow the process from an initial small change in shape. Okay, so if you will see the schematic diagram here, so this is a bar or this is a piece, metal piece you can say. Okay, so the length is L. Okay, the length is L. Maybe you can write the notation in your notebook, because we'll make one numerical today also. The length is L. Okay, and the width is W and the thickness is T. Okay, so here only when we are talking about the strain, that means we have to think about the original strain, the length, and what is the changing length. And after deformation, what you will find? You will find the change in length is dl, okay, and the change in width is dw, and the change in thickness is dt. Only these three things we have to think. And the axes are 1, 2, 3, because in all the x, y, and z axis it is changing, right? This is the basic the assumption. Up to the maximum load, the deformation is uniform. Okay, so because you know normally when we are talking about any metal forming, so we are considering the volume whatever you are putting in the beginning, and the same volume is coming in the output, because everything we are not considering any loss there. So the deformation is uniform, and the element chosen can be large and consider the whole gauge section. So that means we are considering the whole gauge section. We are not considering only one part. Okay, because we are deforming everything, all the metal piece. Okay, and also one more thing, if you are doing, because normally in the laboratory scale it is very difficult, because we need a long sheet, we need a long piece of metal. We cannot take only some metal we will add and we will do some chemical analysis and we will find out. Okay, in laboratory normally it will be difficult because if you will go, or if you will go to the industrial scale or big scale, then probably it will be much more accurate. So during deformation, the faces of the element will remain perpendicular to each other. Okay, so that means what we are assuming, so everything should be perpendicular to each other. That means x is perpendicular to y, y is perpendicular to z, and also x is perpendicular to z. By inspection, a principal element, that is, there is no shear strain associated with the principal direction. So you are not finding any shear strain there. Okay, so this is the basic assumption. During any small part of the process, the principal strain increment along the tensile axis is d epsilon 1 equal to dl by L. Is it correct? Only just we are considering change in length by original length. Okay, and that the increase in length per unit current length. So this one is the basic definition. Similarly, when you have you are considering the length dl by L. Similarly, if you want to consider about the width and the thickness, so you will find d epsilon 2 equal to dw by w, because this is change in width divided by the original width. Similarly, d epsilon 3 equal to change in the thickness divided by the original thickness, right? Fine.
Yes, sir.
Okay.
Yes, sir.
Just you can write down somewhere, very easily. Do not write any text, because I have already shared in the MS Team. Already I have uploaded. Okay, the final one I will upload last, but up to today's class I have already uploaded. Okay, otherwise you can download if you do not want to write. Okay, so next one, when we are thinking what I told just now, when we are thinking any mechanical forming, so the constant volume process we are considering, because whatever the initial volume of the material or the sheet, and also we are considering same, whatever the output you are getting, same means the volume. We are thinking that the volume should be same. So it has been mentioned that the plastic deformation occurs at constant volume, so that the strain increments are related in the following manner. Okay, so with no change in volume, the differential of the volume of the gauge region, so that means the stress equal to force per area will be 0. Okay, so if you want to take the volume, so d volume, what is the volume? So L into W into T equal to d L0 W0 T0 equal to 0. Okay, so if you take the derivative, okay, so you will find dl into Wt plus dw into Lt plus dt into Lw, because you have to take dl first, then again dw, then again dt equal to 0. Fine. So if you divide, maybe, yeah, all the students are requested to mute. Jeffrey. Yeah, okay, fine. Okay, so when we have this equation, dl into Wt plus dw into Lt plus dt into Lw equal to 0. So now you can dividing by Lwt in all this term. Okay, because this is multiplication, you can put a bracket here. Okay, so bracket will be much more easier. If not bracket, then maybe you will be confused. Okay, so if you divide by Lwt in all the three terms, so you will find dl by L plus dw by W plus dt by T equal to 0. Fine. And if this term, what is this term? This is dE1 in the previous slide we have mentioned here. Okay, so that means if you will put this dl by L plus dw by W plus dt by T equal to 0, then you will just put, instead of dl by L equal to dE1 or d epsilon 1 and dw by W plus d epsilon 2, and this term is d epsilon 3 equal to 0. Right, and thus for constant volume deformation, the sum of the principal strengths increments is 0. Okay, and if we will remove this d term, only you can mention that epsilon 1 plus epsilon 2 plus epsilon 3 equal to 0, right? Because this derivation in some books you cannot find. Okay, so that's why I put very simplified, because directly in some books they mention epsilon 1 plus epsilon 2 plus epsilon 3 equal to 0. And this term already we have derived in composite materials. Okay, but still maybe for some new students, I just put this derivation. Okay, is it clear?
Yes, sir.
Okay.
Yes,
Yeah.
sir.
Yeah, fine. So now maybe in the last class also we have maybe somebody was asking about, I think the when we make it, you know, ln h1 minus h0, or maybe ln something we are doing with some numerical, maybe somebody was asking again. So I put here again the derivation actually how you are getting, because at least some students you should know that one, how actually normally we are getting. Otherwise you can follow some books also. So if a block of initial height h0, so that means whenever you have some block, so initial height, let's say you have the h0 and you are making to, or you are deforming to h1, or the compressed to h1. So that means it is changing from height h0 to h1. So how you are getting the true strain? Okay, and the true strain equal to epsilon equal to, because you are changing the height from h0 to h1. So that means integration of change in height divided by the original height. So that means integration of dh by h with respect to, or with from h0 to h1, right? So you will get how much ln, because this equation, for example, if you have this is 1 by h dh, okay, so or h to the power minus 1 dh, you will get ln h1 minus h0, because this is the upper limit, or the and this is the lower limit. Okay, and if you want to convert, because this upper part is h1 and h0, so you can make it minus ln h0 by h1, just you can reverse it. Okay, and that one also, if you want to, like, you know, do in detail how it is coming, still I put some like, you know, notations here. But if you want to go the total detail, how it is changing, why it is changing, what should be the assumption, then you can just follow, you know, the strength of material notes, maybe you know, you have studied in the beginning. Okay, and if you want to find out the conventional strain or the engineering strain, E equal to, okay, how much you will get, because this is change in length by original length. So h1 minus h0 by h0, because both the terms are different. This is the true strain. So that means whatever the change you had, or dh divided by the original length. But here in the engineering strain or the conventional strain, what we are getting the change in strength, a change in height, h1 minus h0 divided by the original height, equal to h1 divided by h0 minus 1. Just you can make h1 by h0 minus h0 by h0. So you will get h1 by h0 minus 1. Is it clear?
Yes.
Yeah, simple one. There is no you know, difficulty here. Okay, and the calculated strain will be negative, whatever you will calculate from here. Okay, so if you will, for example, if somebody, maybe if we will do numerical in future, or maybe you can just find out, you can put some values, whatever the initial height and the whatever the final height. If we will calculate this one, because sometimes we are getting also, like, you know, negative value. So here the calculated strain will be negative. If we will calculate here, whatever the value is given according to your experiment, so this value will be negative and indicating the compressive strain. Okay, so that means if the value you are getting negative, you are finding there is a compressive strain. Do not worry that this my result is coming negative. Okay, however, in metalworking problems, it is common practice to reverse the convention so that the compressive stresses and strains are defined as positive. So if you are getting some negative value there, so you can find, or you can note it somewhere, that there is a compressive strength there, but we are assuming this is as positive because it's a metalworking process. Right, you have to write positive. Do not think that whenever we are getting negative means my numerical or my calculation is wrong. Okay, so when using this convention, we shall use the subscript c. So when you have, or when you are getting the negative value and we are considering the positive, so at the similar way, for example, if you do not write the, like, you know, note this is the negative value, so we are considering as positive. If you do not want to write, just you can make the subscript c. Okay, for example, if you are thinking about the strain equal to ln h0 by h1, if initially we had epsilon c equal to ln h0 by h1, okay, so what you will do, you have to write ec equal to, okay, so you can see what is the e value. E value is h1 minus h0 divided by h0. Okay, so you will make it positive. So I will make it positive, just you can make it reverse. So h0 minus h1 divided by h0, but you can make it here c. Okay, so similarly here ec also. Okay, what is the value of e? So E is ln h1 by h1 divided by h0. So you can make it here epsilon c equal to ln h0 by h1. So that means we can consider, or we will understand that this value was negative and we are considering as positive here. But if you do not write the epsilon c also, bracket you have to write everything. But this one will be easier, right? Is it clear?
Yes, sir.
Okay. Yeah. Okay. So this derivation also shows here, like, you know, whenever we are making the volume change or maybe the constant volume or whatever the metal you are putting inside the die or inside the metal forming process, then we are finding some like the output or the product. So here also another factor is coming, a reduction in cross-sectional area, because whenever we are talking about the stress force per area, so at the similar time, because you are not deforming whole the piece, you are deforming a small portion which is coming within that die or within that metallurgical zone, right? So also we are considering the reduction in cross-sectional area. So the fractional reduction is R equal to, okay, the fractional reduction we are considering R equal to whatever we have done here, let's say. Okay, here the EC, whatever we have found out here, the fractional reduction R equal to the initial area divided minus the change in area divided by the initial area. Okay, so you can put that R equal to A0 minus A1 divided by A0. Okay, and the next one we have from the constancy of volume relation. Okay, what we are talking about, the volume, initial volume and the final volume should be same. So if you are considering the volume, so this A1 L1, because this is area, so you do not need to write one more factor. So initially we have considered T, W and L. Okay, so here instead of A, we just mentioned again, instead of TW, we mentioned the area. So area into length, because this is volume, equal to A0 L0. So here if you want to calculate R equal to 1 minus A1 by A0. Okay, or A1 by A0, because you can just make it this one in the right hand side or the left hand side, A1 by A0 equal to 1 minus R, right? Similarly, epsilon equal to ln L1 by L0 equal to ln A0 by A1 and equal to ln 1 by 1 minus R. Okay, take 1 minute and you can think whether you can find out this one or not. Okay, because you have the R initially here. Okay, so R equal to A0 minus A1 by A0, right? So if you divide A0 by A0, so you will find 1, right? Minus A1 by A0, right? Is it clear? And here also, if implies or A1 by A0, you can put in one side LHS or RHS equal to 1 minus R, right? Similarly, this one already we have done here, but if you do not remember, epsilon equal to ln L1 by L0. So that means whatever the change in length by the original length equal to, if this value L1 by L0, you can take here L1 by L0 equal to A0 by A1. So instead of L1 by L0, you can put ln A0 by A1, right? So A0 by A1 is how much? This value A0 by A1 equal to 1 by 1 minus R, the opposite one. So equal to ln 1 by 1 minus R. Fine. Is it clear?
Yes, sir.
Just we put these terms here and that term there. So you can write it down, this small equation. Then we have one numerical now. You can just do. So 1 second. No, maybe after one slide I have a numerical. Okay. So is it clear up to this derivation?
Yes, sir.
Okay. So this is all about the mechanics of metalworking. Okay. Yeah. So now when we know the mechanics of metalworking, we know the parameters. So now the requirement of the theory describing the mechanics of metalworking process, the ability to make an accurate prediction. Okay, so one more thing you are getting, maybe you are aware of, maybe in the beginning, I think I asked you about some simulation. I think you were telling that ANSYS and everything you were told. So now also you have to think about why we are using some simulation kind of work. So you have to make some accurate prediction. Okay, you cannot tell that just roughly I'm doing something, because now you are going towards maybe final year, then you will be an engineer maybe after 1 year, right? So you have to think accurately. You cannot tell, because sometimes when we are asking in the class, maybe many times we are telling a lie, as a student, if I will ask why you have not submitted, so this is, so many excuses you will tell. But now you have to tell accurately, okay? Because whenever you are doing anything, you cannot tell somebody lie, because somebody has a lot of experience there in the company. Because if you are in the in the shift or maybe shift in charge, for example, initially, or maybe assistant manager, so maybe the upper in GM level or maybe in DGM level, so they will ask and they will see. Okay, the moment they will see, they will tell that what kind of composition is there, or how much length will be coming, how much thickness. Because for the initial level, we have to measure everything, because we are not very not very accurately predicting there. Okay, so because they have worked a long time there, so they can know immediately when they are looking. Okay, so you have to accurately predict that one of the stresses, strain and velocities at every point, and the various approaches differ in complexity. So one more time also, I remember I told you, for example, I gave the same example, the iron melting. Okay, for example, the iron melting, you are theoretically we are considering 1539 degrees centigrade. But if you are going to any kind of like iron melting furnace, maybe sometimes maybe exactly you can get maybe if you are lucky, but sometimes it will vary, maybe within 10 to 15 degrees C it will vary. So similarly here, whenever we are approaching many other processes or many other applications, so it will differ in complexity and in the degree to which they meet this requirement. Okay, for example, if our goal is same, let's say X student or maybe Y student, both goal is same, but whenever also we are doing or following the process, you will find little differ. Maybe I will find little differ, right? And in general, such a theory consists of three set of equations. Okay, so what are the basic equations? So one is the static equilibrium of force equation. Okay, and what is the static equilibrium force equation? The residual stress system existing in a body must be in static equilibrium. Okay, maybe these are every time we are talking about the equilibrium or the volume constant. Thus, the total force acting on any plane, okay, whatever the total force acting on the plane through the body, and the total moment of forces on any plane must be zero. Okay, what we have discussed in the mechanics. And the second one, we have the Levi-Mises equation expressing a relationship between stress and strain rate. Okay, that also stress and the strain rate already also we have discussed, like the flow curve and the flow stress and also the average flow stress, right? And this states that what actually maybe I do not know whether we will cover this one or not. Maybe I think not necessary. So I put one definition here. This states that the ratio of the strain increment, the ratio of the strain increment will be the same as the ratio of the deviatoric stress. Okay, probably we will cover, I think, the hydrostatic stress maybe in the module 1. I think we will cover that one. So I mentioned here what is the deviatoric stress, the components of stress remaining after subtracting the hydrostatic stress. Okay, so hydrostatic means the average of the principal stress. Okay, so this one maybe I will put one schematic diagram, what is hydrostatic stress, maybe in the next module. Okay, and the third one we have the yield criteria, and the yielding would occur when the greatest maximum shear stress reaches a critical value. So that means the maximum limit you have to go. Okay, beyond that you cannot go. Maybe it will go to the fracture side. Okay, so these three set of equation you have to consider whenever you are going to the mechanics of metalworking. Fine. Yeah.
Yes, sir.
Okay. So now you have to do one numerical here. So I will not show. Just you can. Maybe I don't know whether the answer will show you. Yeah, just you can read the last line. Okay, determine the engineering strain, to strain and a reduction for a bar which is doubled in length. Okay, so first one you have to calculate. Just only one line. Then second question I have B. Determine the engineering strain, true strain and a reduction for a bar which is doubled in length. Only one line numerical. You can just read the question again. Have you read the last line? I just compressed it. Yeah, the example 4. Can you see this line?
Second line, sir.
No, the first line. Example 4,
Yes, sir,
first
we
line.
can see, sir.
Yeah.
Yes, sir.
Because the answer is there, so that's why I just stopped it. So you can just do. If not, then I will show you. Maybe take 3-4 minutes. Determine the engineering strain, to strain. Okay, just you can write the given. Okay, what is the value is given? Value is given a bar which is doubled in length. Okay, so there is nothing written deforming something, so you have to understand it's a deformation process. Okay, so a bar which is doubled in length, so that means you will find the given value here, doubled in length. So you have to calculate the engineering strain, true strain and the reduction. Three things you have to calculate. Then second part is there also, so first part you can do. If you want to show the see the equation, then I will go back. Just you can tell me, or maybe you can download from the MS Team. Already I have uploaded, but do not see the answer. Answer is there. Do not see. You can just try. Then if not, then you can see. Can somebody tell what is the given value?
They're given like L1 is equal to 2L0.
L1 equal to
2L0.
Yeah.
Sir, it's like the engineering stain 1,
Yeah.
true stain is 0.693 ln 2,
Yeah.
and
And
reduction is 0.5 half.
Fine. Yeah. Other students, please do. Charles already have done it. And Charles, also you can do the next part is actually a bar which is halved in length.
Okay, sir.
Other students, please, if not, then I will show you or I will explain you. So, but please try. Maybe 2 minutes you can take and please try. Then I will explain. First, you have to write the given. Amal, are you getting?
Yes, sir.
Okay. So, given value you understood. Now, if given value you know, then all the equations are there. You have to find out E, then epsilon, then R. Three things you have to get it. Aditya, Vishnu. Yeshwant, Anirudh, are you doing?
So could you show the formula for engineering strain?
One second. Yeah. This slide
Yes, sir.
or the upper one also will get here. Just I will little. Yeah. These are the small like numerical you can do now, because in if you when we will go to the rolling and forging, so you will find a big numerical, a little long lengthy. Okay, so you can practice now. It will be better for you. And initially also maybe for the new students, I'm just telling, whenever you are writing given, you have to write very clearly. Okay, for example, R, let's say, okay, the fractional reduction or maybe reduction you can write. Okay, then A0, let's say, initial area. Okay, you can write initial area equal to A0 equal to this much. A1 equal to the change in area equal to A1 equal to this much. Right, you have to write. Then, for example, H1, let's say, or maybe the H0. H0 equal to the initial height. H1 equal to the change in height. Then H1. Then the value you have to put.
So for second part, is it like 0.5 compressive, 0.693 compressive, and R is -1, again compressive.
E is 0.5, right?
Yes, sir.
And
Negative, so compressive.
epsilon is negative.
Uh, 1 second.
You can check. I think both two are negative. One is positive.
I'll check.
Yeah, you can cross. Maybe you can check. Maybe I'm wrong. Probably you can again check. Other students only except Charles. Nobody. Vishnu, what happened? Mohilan.
Sir, it's negative only, sir.
All the three are negative?
Yes, sir.
Okay. Okay. No one? Okay. Okay, fine. So I will show you. So the first part you can see here. Okay. So can you see the screen? So for a bar which is doubled in length, okay, so doubled means, for example, here we have taken L1 and L2. Okay, so that means the bar, like whatever the output is actually doubled from the initial one. Okay, so what Charles has taken L0 and L1, or maybe L0 and L1, but here we have taken L2 and L1. Okay, so you have to write initially what is the L1 value and what is the L2. So the given value is L2 equal to 2L1, right? And the equation, if you will put here, okay, the E equal to L2 minus L1 by L1. So you will get, instead of the L2, the 2L1 you can put here. So 2L1 minus L1 divided by L1. Okay, so if we'll calculate here, so that means 2L1 divided by L1 minus L1 by L1. So you will get the value of 1, right? Is it clear up to now?
Yes, sir.
Yeah. Then second is epsilon, if you want to calculate ln L2 by L1. So instead of L2, you can put 2L1. Okay, so you will get ln 2L1 by L1. So you will get 0.693. Okay, because the ln2, you have to take ln2 equal to 0.693. Maybe you can cross check, maybe some value, a little bit of mistake. And then the reduction equal to R equal to A1 minus A2 divided by A1. So you will get A1 by A1 equal to 1 and minus A2 by A1 equal to 1 minus. Okay, so L1 divided by L2. Right, and this equation you will get from the that slide I have shown you in the here. Okay, you can take this value. So if you take this value, so you will get 1 minus L1 by, because L2 is 2L1, so L1 by 2L1, you will get 0.5. Right, is it clear, the first part? Yeah. So
Yes, sir.
so second part, can you do? Just take again 2 minutes. So the question is, determine the engineering strain, to strain and the reduction of a bar which is halved in length. So the first one, it was doubled, but this one is halved in length. Is it difficult, these numericals? Only the equation, very small equation. We are not doing maybe in rolling forcing. When we'll go, probably we'll find little difficult because very lengthy. Okay, but these are very small. Only the equation, 3-4 equation only you have to remember. Of course, this is online now, so all the formulas are with you only. Okay, but only you have to write, because again I am telling the same thing. If you are writing the given, then what should be the find out, or maybe what to find out, then it will be very easy which formula you will put. But if you are not writing anything, you are just because many students, they are only focusing on the answer. Okay, just they are putting the values there. They want actually the answer. So you do not worry about the answer. If the steps are correct, if answer is wrong also, you do not need to worry. Okay. Have you done?
Yes, sir. Done.
Yeah. How much, Amal?
Sir, I'm getting minus 0.5 minus 0.693.
Yeah. And the reduction?
Sir, I think -1.
No, negative how much?
-1, sir.
Oh, -1. Yeah. Okay, you can see here. Maybe other student, again I'm explaining. For a bar which is decrease in length, so L2 equal to L1 by 2, because it is mentioning that halved in length. Okay, so L2 equal to L1 by 2. So you can put the equation E equal to L1, because you can put, instead of this L2, L1 by 2 minus L1 by L1. So you will get minus 0.5. Okay, so you can put, maybe Charles also, you can correct it when you have minus, I told you. So you have to make it EC equal to, so you can make it positive. Okay, just reverse L1 minus L1 by 2 by L1 equal to 0.5. Right. Similarly, if epsilon equal to ln L1 by 2 divided by L1 equal to ln 1 by 2, you will get around minus 0.693. Okay, similarly, R equal to 1 minus L1 by 2 equal to minus 1. Okay, so if this is reversed already, so then you do not need to change. If this is already reversed, you can put it minus. If this is not reversed, you can put it as a plus. Or here also, if not reversed, you can make it as epsilon c equal to this much. Okay, fine.
Yes, sir.
Yeah. So now one more slide. I have the analysis method, because many students they were probably like they are much more interested about the analysis part, because sometimes we are now in this generation we are many researchers we are thinking of the simulation kind of work. So I just put if somebody is interested, maybe you can work on it, or maybe they can think also when we are talking about the ANSYS or maybe the FEM. So we are thinking only one part. Okay, but similarly also if you will merge, maybe I asked this question in the beginning, why actually. So the ANSYS also you can use many places. Similarly in FEM also you can use in many places. Okay, so in the general case there are 9 independent equations containing 9 unknowns and the 6 stress. Okay, so these components also we are not considering here because we are not going to that detail, because already in composite I think we have covered whenever we are talking about all the stresses and all the strain. Okay, we are not covering here. While an analytical solution is possible if a sufficient number of boundary conditions are specified, the mathematical difficulties in general solution are formidable. So for example, whenever we are doing any kind of experiment, so we are not finding sufficient data there. So to overcome that one, so what we are doing, we are going to any kind of simulation kind of work. So all the big database is there. Okay, so with the help of that database, we can find out or we can analyze something. So thus the most analysis of actual metalworking process are limited to 2-dimensional or the symmetric 3-dimensional problems. Okay, so apart from this also, if you want to go beyond that one, probably we cannot access that one. In that case, of course, you have to go for the only experimental. But this experimental also you cannot do very accurately in the laboratory scale. You have to go to the industrial level, because big sheet whenever it is coming, so you will find the accurate data there. So the method of analysis in increasing order of complexity and the ability to predict the fine details are. So there are so many processes are there. One is the slab method. So that means you are assuming the homogeneous deformation, what we have done up to now. Then second one, you have the uniform deformation energy method. Okay, so that you are calculating the average forming stress from the work of the plastic deformation. You are calculating the average forming stress. And third one, we have the slip line field theory, permits point by point calculation of stress. For example, if you will go to the that the weather forecast, so they are doing every second or every minute. So here also we are calculating point by point calculation of the stress for plane strain condition. And the fourth one, we have the upper and lower bound solution based on the theory of limit analysis, uses a reasonable stress and the velocity field, and to calculate the bounds within which the actual forming load must lie. And the last one we have, I think many students, they are focusing on the finite element method. A technique called the matrix method allows large increments of the deformation for rigid plastic materials. Okay, but you have to focus on, or you have to think on the computational time also, because if you cannot fix that parameter, then again you will not find in a proper way. So you have to fix in that particular time, then only you can calculate. So these are many methods are there, many analysis process are there. So that's why I put this slide, because you do not think that only the ANSYS or the FEM or maybe any kind of software, you are focusing on that area. So total, I think whole mechanical process, I think also we can use. Okay, so that's the main basic reason I put this slide to understand. Do not think that only my whatever I have studied, maybe ANSYS or maybe some other software. This is not for only one purpose. Maybe you can. That's why we are thinking about now the application of whatever you have studied in our mechanical or maybe in the related subject. So that's why then only you have to be much more serious or much more interested in that particular software. Okay. So this is all about from my side. If you have any question, you can ask.